Hello everyone, my name is V Dinesh and my roll number is 536 and my topic is the future is big graphs, a community view on graph processing systems. Graphs are by nature unifying abstractions that can leverage interconnectedness to represent, explore, predict, and explain real and digital world phenomena. All our real users and consumers of graph instances and workloads understand these abstractions. Future problems will require new abstractions and systems. Big tech companies such as Google, Facebook, and Microsoft have introduced various systems for managing and processing the growing presence of big graphs. Data flows in the form of in from diverse sources, already graph model as well as non-graph model, and is persisted, managed, and manipulated with online transactional processing (OLTP) operations such as insertion, deletion, updating, filtering, projection, joining, uniting, and intersecting. The data is then analyzed, enriched, and condensed with online analytical processing (OLAP) operations such as grouping, aggregating, slicing, dicing, and rollup. Finally, it is disseminated and consumed by a variety of applications, including machine learning, such as ML libraries and processing frameworks, business intelligence (BI), such as report generating and planning tools, scientific computing, visualization, and augmented reality for inspection and interaction by user. Abstractions. Abstractions are widely used in programming languages, computational systems, and database systems, among others, to conceal technical aspects in favor of more user-friendly, domain-oriented logical views. Currently, users have to choose from a large spectrum of graph data models that are similar but differ in terms of expressiveness, cost, and intended use for querying and analytics. Understanding data models. Today, graph data management confronts many data models, directed graphs, RDF, variants of property graphs, and so on, with key challenges. Deciding which data model to choose per use case and mastering interoperability of data models where data from different models is combined. Figure example lattice shows graph data model variants with the model characteristics as shown in the given figure. In this figure, we can see that lattice shows graph data model variants with the model characteristics. Studying studying one requires foremost investigators working with data and data models, which is uncommon in the data management field and should be conducted collaboratively with other fields such as human computer interaction (HCI). Work on HCI and graph exists. For example, in HILDA workshops at Sigmod. However, these are not exploring the search space of graph data models. Studying 200 can build on existing work in database theory, but can also leverage findings from neighboring computer science communities on comparison, featureization, graph summarization, visualization, and model transformation. As an example, graph summarization has been widely exploited to provide succinct representation of graph properties in graph mining, but they have seldom been used by graph processing systems to make processing more efficient, more effective, and more user-centered. Algebraic operators for graph processing. Currently, there is no standard graph algebra. The outcome of graph query language GQL standardization project should influence the design of a graph algebra alongside existing and emerging use cases. However, next generation graph processing systems should address questions about their algebraic components. A relational like graph algebra able to express all the first order queries and enhanced with a graph pattern matching operator seems like a good starting point. However, the most interesting graph oriented queries are navigational, such as reachability queries, and cannot be expressed with limited recursion of relational algebra. Furthermore, relational algebra is a closed algebra, that is, inputs and output of each operator is a relation, which makes relational algebra operators composable. Current graph query engines combine algebra operators and add HOC graph algorithms into complex workloads, which complicates implementation and affects performance. An implementation based on a single algebra also seems utopic. A query language with general Turing machine capabilities, like a programming language, however, entails tractability and feasibility problems. Algebraic operators that work in both centralized and distributed environments, and that can be exploited by both graph algorithms and ML models, such as GNNS, graphlets, and graph embeddings, could be highly desirable for the future. Ecosystems. Ecosystems behave differently from systems of systems. They, they couple many systems developed for different purposes and with different processes, standards for data models and query languages. Graph processing ecosystem standards can provide a common technical foundation, thereby increasing the mobility of applications, tooling, developers, users, and stakeholders. Standards for both OLTP and OLAP workloads should standardize the data model, the data manipulation and data definition language, and the exchange formats. They should be easily adaptable by existing implementation and also enable new implementation in SQL-based technological landscape. It is important that standards reflect existing industry practices by following widely used graph query languages. To this end, ISO or IEC started the GQL standardization project in 2019 to define GQL as a new graph query language. GQL is backed by 10 national standards bodies with representatives from major industry vendors and support from the Property Graph Committee as represented by the Linked Data Benchmarks Council. Dynamic and streaming aspects. Future future graph processing ecosystems should go with dynamic and streaming graph data. A dynamic graph extends the standard notion of a graph to account for updates, insertions, changes, deletions, such that the current and previous states can be seamlessly queried. Streaming graphs can grow indefinitely as new data arrives. They are typically unbounded. Thus, the underlying systems are unable to keep the entire graph state. The sliding window semantics allow the two notions to be unified, with insertions and deletions being considered as arrivals and removals from the window. Performance. Graph processing raises unique performance challenges from the lack of a widely used performance metric other than response time to the methodological problem of comparing graph processing systems across architectures and tuning process to performance portability and reproducibility. Benchmarks, performance measurement, and methodological aspects. Graph processing suffers from methodological issues similar to other computing disciplines. Running comprehensive graph processing experiments, especially at scale, lacks tractability, that is, the ability to implement, deploy, and experiment within a reasonable amount of time and cost. Even seemingly minor HPAD variations, for example, the graph's degree distribution, can have significant performance implications. Graph processing systems rely on complex runtimes that combine software and hardware platforms. It can be a daunting task to capture system on the test performance, including parallelism, distribution, streaming versus batch operation, and test the operation of possibly hundreds of libraries, services, and runtime systems present in real world deployments. That's it. Thank you, everyone.